over darkness. I humbly request our esteemed dignitaries on the dais to kindly come forward for the lamp lighting. Request all the dignitaries to please stay for a group photograph. Thank you to all our dignitaries. May this light continue to guide us towards learning, innovation, and excellence. May I now humbly request all of you to join us as we begin the felicitation ceremony to honor the distinguished dignitaries gracing this occasion. May I now invite our respected director, Professor R.K. Sharma, sir, to please come forward and felicitate Honorable Vice Chancellor, Professor Anand Srivastava. Thank you, sir. I invite the co-patron, Professor Vishal Bhatnagar, HOD CSE, to felicitate guest of honor, Professor D.K. Lopial, sir. Thank you, sir. I now invite Program Chair Professor Manoj Kumar to felicitate Honorable Director Professor R.K. Sharma. Thank you, sir. I invite Conference Chair Professor Nanne Singh to felicitate Professor Vishal Bhatnagar, HOD CSC. Thank you, sir. I invite the General Chair, Dr. Ram Shringar Rao, to felicitate Professor Sanjoy Das, General Co-Chair. Thank you, sir. I invite the organizing co-chair, Dr. Vishal Gupta, to felicitate General Chair, Dr. Ram Shringar Rao. Thank you, everyone. Moving ahead, I now take the privilege of inviting the driving force behind this conference, Dr. Ram Shringar Rao, whose leadership and dedication have been instrumental in organizing this conference. Sir, I request you to kindly come forward and grace the stage.
Hello. Thank you, uh, dear Anushka. कोशिश दमदार होनी चाहिए। कोशिश दमदार होनी चाहिए। वक्त और किस्मत दोनों ही बदलते हैं। Thank you. Today's chief guest and chief patron of the conference, Professor Anand Srivastava, Honorable Vice Chancellor. Guest of honor, Professor D.K. Lobia. Respected Director, Professor R.K. Sharma, patron of this conference. HOD CSC, Professor Vishal Bhatnagar, co-patron of this conference. HOD CSC, Professor Sanjay Das, co-general chair from Indira Gandhi National Tribal University, a central university. Regional Center Manipur. And Professor Nanne Singh, conference chair. Professor Manoj Kumar, program chair. HOD EC, Professor S.K. Dana. Dr. Suresh Kumar, organizing chair. Dr. Professor Richa Bhatia. Professor Amita Jain. Professor Vishal Gupta. Professor Bharti Nagpal. Honored all the faculty members, distinguished guests, eminent keynote speakers, eminent researchers, industry expert, media persons, faculty members, officers, authors, and dear students. It gives me great pleasure and honor to welcome you all most cordially this morning at the official opening of the 5th International Conference on Advanced Computing and Intelligent Technologies, ECACIT, ICIT 2026, jointly organized by Netaji Subhas University of Technology and Indira Gandhi National Tribal University, Regional Center Manipur, Imphal. Ladies and gentlemen, over the past 2 years, our university has significantly enhanced its academic landscape by organizing a suite of high-impact events, including an international conference, providing a global research platform, specialized faculty development programs, elevating faculty expertise in pedagogy and emerging technologies, hands-on workshops aimed at skill enhancement, and expert lectures linking industry professionals with our students. These efforts were further complemented by a practical industrial visit, fostering a robust industry-ready academic environment. This is second international conference within the year, even though within the 6 months. This indicating a strong focus on professional development, knowledge dissemination, and industry academia linkage. Today, we gather not just to attend a conference, but to celebrate innovation, collaboration, and the relentless pursuit of knowledge. The rapid transformation of our world through artificial intelligence, intelligent communication system, data science, IoT, and smart computing systems. Forums like ICACIT, ECACIT, serve as an essential platform where ideas evolve into impactful solutions. What makes this moment even more special is that we are celebrating the 5th edition of ECACIT. Over the past few years, this conference series has grown steadily and bringing together brilliant minds from academia, research institutions, and industry across the globe, following the successful conferences held in New Delhi, then Manipur, then Sila, Italy. And this time, we are organizing this conference here in Delhi, again in Netaji Subhas University of Technology. Each edition has contributed to building a vibrant community of researchers dedicated to advancing the frontiers of computing and intelligent technologies. The journey of ECACIT has been one of continuous growth and academic excellence. The earlier editions successfully fostered discussions, and emerging technologies, encouraged interdisciplinary collaborations, and provided young researchers with a global platform to present their innovative work. It is inspiring to see how this conference has evolved into a recognized forum for exchanging groundbreaking research and visionary ideas. The theme of this conference highlights the importance of advanced computing and intelligent systems in shaping the future of society. I'm delighted to share that this year, the conference received an overwhelming response with a total of 547 research papers submissions from researchers across countries like USA, Taiwan, UAE, Uzbekistan, and from major states across India like Tamil Nadu, Assam, West Bengal, Rajasthan, Punjab, Uttarakhand, including Delhi NCR, reflecting the global interest and relevance of this domain. After a rigorous and quality-driven review process, only 80 papers were accepted, resulting in a highly competitive acceptance rate of approximately 15% only, which clearly demonstrate the technical strength and quality orientation of this conference. We are especially proud to highlight that our university, NSUT, has contributed in large numbers. And we have received 26 research papers. And due to some restriction and Springer guidelines, only 6 best papers has been accepted. Sir, we are so proud that all these papers were technically soft and high quality research papers. Enhance institutional excellence by fostering a robust research culture and elevate academic standards through rigorous peer-reviewed contributions by ensuring a sustainable, diverse, and competitive research environment in the campus, in NSUT campus. Over the next 2 days, ICASIT 2026 will feature thought-provoking keynote talks, technical paper presentations, and engaging discussions covering diverse areas such as artificial intelligence, machine learning, deep learning, intelligent networks, cybersecurity, Internet of Things, and smart systems. I am confident that these sessions will spark new ideas, inspire collaborations, and open new research directions. We would like to express our sincere gratitude to our eminent keynote speakers from different countries. Professor Nottingham Trent University, Nottingham, UK, Dr. Om Prakash Kavartia from Nottingham Trent University, UK, Mr. Praveen Kumar Pal, Nokia of America Corporation, USA, Mr. Tarun Kumar Chatterjee, Presidio, USA, Mr. Ashok Malempati, Kemper Corporation, Chicago, USA, Mr. Pawan Kumar Sangwan, IT Chapter Lead, ING Bank, Netherlands, Professor D.K. Lobial, JNU, and Professor Vijeta Gautam, Chaudhry Charan Singh University, Uttar Pradesh. We would like to express our sincere gratitude to our technical program committee members, reviewers, and organizing team whose dedication and hard work have made this conference possible. We would also like to extend my special thanks to our esteemed editors and contributors, Professor Vincenzo Piuri, professor at the University of Milan, Italy, Professor Monica Bianchini, associate professor at the University of Siena, Italy, Professor D.K. Lobial, professor at the School of Computer and System Sciences, JNU, and Professor Sanjay Das from Indira Gandhi National Tribal University, RCN Center, Manipur, Imphal, for their tireless efforts and invaluable contributions in making ICASIT a successful and high-quality academic platform. Our special thanks also goes to all the authors and the participants who have contributed their valuable research and chosen ICASIT as the platform to share their excellent work. Our heartfelt and special thanks to Honorable Vice Chancellor Professor Anand Srivastava for his visionary leadership, unwavering support, and providing necessary approvals that enabling the smooth execution of this conference. We also thanks to our visionary director, Professor R.K. Sharma, Professor Vishal Bhatnagar, Professor Manoj Kumar, Professor Nanne Singh, Professor Rasmi Gupta, Dean Students Welfare, Professor Aarti M.K., Dr. Suresh Kumar, Dr. Vishal Gupta, and all our computer science faculty members, electronics faculty members, and all the distinguished officers, staff, and research scholars and students who have contributed a lot to organize this conference. My sincere and special thanks to our PhD and MTech scholars, especially Dr. Manish, Anushka, Mukesh, Magnita, Rakesh, Vidhu, Vandana, Sanjana, and all the MTech students and BTech students who have made this conference possible. We encourage all participants to actively engage in discussions, building collaboration, and make the most of this opportunity. Once again, we warmly welcome all of you to ICASI 2026, and we wish you an inspiring, productive, and memorable conference experience. Thank you, and we look forward to the exciting discussions and sessions, please. Thank you so much.
Thank you, sir, for giving us a clear and insightful overview of the conference objectives and vision. At this moment, I have the distinct honor of inviting the pillar behind this conference, Professor Sanjoy Das, whose constant support and dedicated efforts have played a vital role in the successful organization of this conference. Before inviting him for an address, let me share a brief introduction about his remarkable professional journey. Professor Sanjoy Das is currently serving as a professor and head of the Department of Computer Science at Indira Gandhi National Tribal University Regional Campus, Manipur in Amarkantak, a central government university of India. Before joining IGNTU, he served at reputed institutions including Galgotias University, GB Pant Engineering College, and Assam University Silchar, contributing significantly to academic development and research culture. His research interests include ad hoc networks, distributed systems, and Internet of Things. Sir has authored more than 100 research publications in Scopus, Web of Science, and SCI Index Journal and conferences, and edited several academic books and holds multiple national and international patents. He has actively contributed to organizing and chairing numerous international conferences and continues to play a vital role in advancing collaborative research and innovation. May I now request Professor Sanjoy Das to kindly come forward and address the gathering. Ladies and gentlemen, please welcome sir for the address.
Thank you, Anushka, for your brief introduction about me. Good morning, everyone. This distinguished guest, the chief guest of the program, Professor Anand Srivastav, the Honorable Vice Chancellor, NSUT New Delhi, the guest of honor, Professor R.K. Sharma, Director, NSUT East Campus, guest of honor, Professor D.K. Lobial, School of Computer and System Sciences, JNU New Delhi, special invitees, the respected faculty members of this institution and faculty members from other universities and institutions joining in this gathering. Very warm welcome to all of you. And I'm truly honored to welcome each of you in this prestigious conference. Your gracious presence definitely add very innovative things to do in this conference and today marks a significant occasion as we come together to share knowledge, exchange ideas, and inspire one another. First, I would like to express my gratitude to the Director of IGNTU, Professor Angie Nellingam, and the Vice Chancellor Sir of NSUT and the Director of NSUT East Campus for facilitating the collaboration between both institutions to organize this event. And unfortunately, the Director of IGNTU RCM could not present here due to his prior commitment to other events. So he expresses gratitude to all the faculty members and organizing team and convey his best wishes for grand success of the event. And I take this opportunity to introduce the IGNTU RCM briefly, because in this gathering, very few members of persons may know this campus exists in Northeast. Because this IGNTU Indira Gandhi National Tribal University, you all know it is exists in Amarkantak, Madhya Pradesh, but it is the only one regional campus which is exist in Manipur, and it is located in a very beautiful hilly landscape where we have the campus area is around 301 acres one, and it is still in developing phase. So we are facing a lot of hurdles to organize events on this area, and it is also nowadays it is disturbing area. Although the campus is located in this beautiful landscape and the natural beauty, the fresh air, the scenery surrounding helps student and stay relaxed and focused and fostering both academic excellence and personal well-being. The campus offers range of postgraduate and this doctoral program, especially on the area of art and sciences like political science, social work, physical education, computer science. So we have only 7 departments there, which is running, and all are PG and doctoral programs, though graduation level programs. So now our always the campus is always look for the strong emphasis on research related to the tribal culture, livelihoods, and science and technology to enhance the quality of the tribal dominating area, especially in the Northeast. And Indira Gandhi National Tribunals always committed to excellence in education, innovation, and holistic development. With a strong foundation of academic rigor, a vision for the future, we strive to nurture young mind, encourage critical thinking, and promote research and creativity. And this conference is yet another step in our journey toward intellectual growth and collaboration. This conference was first hosted in 2021 by ADRS Society along with the Manipur campus and other international university, and later on its popularity is day by day is increasing, and many international and national university are collaborating together, and different places of India we have organized this event. Now this is we are really blessed to organize this ICSCIT 2026 in this campus, and this is all initiative is taken by Dr. R.S. Rao, who is the General Chair, Professor Nanda Singh, and another faculty member, Punia sir, who's this conference we are successfully organizing here now. Now, a special thanks I would like to convey. I would like to thank Dr. Narendra Bose, the executive editor of the Strangers, for approving the publication of the papers presented in the lecture note of network and the system book series, which is Scopus Index. And once again, I warmly welcome you all and wish the conference great success. And I am confident that today's session will be enriching and thought-provoking. Let us make the most of this opportunity by actively engaging with and learning from each other. Thank you very much.
Thank you, sir, for your valuable words. Your support and contribution to this conference is truly appreciated. Now I would like to invite our respected head of the Department Computer Science and Engineering, Professor Vishal Bhatnagar, to kindly address the gathering and share their valuable insights.
Good morning, Honorable Vice Chancellor, Sir, Professor Srivastava, Guest of Honor, Professor D.K. Lobial, our Director, Sir, Professor R.K. Sharma, Joy, Sir, from RC, that is Regional Campus Manipur, our faculty members, students, staff. At this time, I would like to first of all start with the thanks to our Honorable Sir, because last week when we visited me along with Nanya Sir and Rao Sir, Sir was very generous and said, "अरे मैंने बोल तो दिया तो मैं आऊँगा, आप लोग इतने दूर क्यों आए दोबारा?" So thank you, Sir. Thank you very much for being so kind. Whenever during this past 2-3 weeks, we have given a lot of things on an 11th hour to be approved by Sir, and Sir have been always kind and considerate to approach the same generously. Thank you, sir. Thank you so much for the same. And at the same time, I would like to thank our director sir also. जब भी मैं sir के पास जाता हूँ तो he always says कि हाँ ये definitely करना है. And this conference is a platform which I had a discussion with our faculty members 2 days back also in the department that this will. I'm really thankful to all our faculty of CSC department who have been always on toes to make some of the other events happen in our department with the small strength of sir 11 faculties. We are trying our level best to organize guest lectures, conferences, FTPs, and to inform everyone. Today also last night, ma'am, Dr. Amita Jain has got a project from AICT. So we are trying our level best to be at the mainstream. Thank you. Regarding the conference, it's a platform. I had a good discussion, sir, when I took the class during last week with the students to inform that this is something, this is a platform which will help them to know out of the box things rather than just getting the idea about what actually is there in the books or which has been delivered. So to gain insight into what currently is going on in the field of intelligent technologies, computing, we need to be more, you can say, associated or more having discussions in like open forums. And this is one of the platform in which we can be more expressive and able to get information in a much better way with the full discussions and active involvement.
Us virtually from Nokia of America Corporation, USA. Before we begin the session, I would like to take a moment to introduce our esteemed speaker. Mr. Praveen Kumar Pal is a software engineer at Nokia of America Corp with over 20 plus years of experience in optical communications and AI/ML based network optimization and embedded systems. Mr. Pal's research covered AI/ML, generative AI network protocols, and high-speed optical standards, including IEEE 802.3400. His interests also extend to wireless systems, IoT, and embedded real-time applications. He is keen on exploring and supporting high-quality research that advances AI-driven networking innovations for the next decade of intelligent communications. Today, he will be delivering an expert talk on the topic quantum-aware optical network architectures for ultra-high capacity communications, which is highly relevant in the context of next generation communication systems. Sir, we warmly welcome you and request you to kindly take over the session and to cover the session in the next 15 minutes. Thank you, sir.
Yeah. Thank you. Can you please allow me to share the screen?
Yes, sure, sir.
Yeah.
Yes, sir, now you can share the screen.
Yeah, I see that. All right. So good afternoon, everyone. I am Praveen Parwal, working as a software engineer at Nokia USA. And today I'm excited to discuss about the latest and latest technology. It is one of the most disruptive and defining technology shifts of our time. A shift that will transform and fundamentally redefine the way we develop and design optical systems. So any guesses? So yes, it is quantum computing 2.0 and digital twin technology. So quantum computing is not merely an advancement, it is the revolution. It will be fundamentally transform how we design, develop, and emulate manufacturing optical systems. By integrating quantum computing with digital twin technology, we are moving toward an era where optical hardware can be modeled with near perfect physical accuracy, optimized in real time, and manufactured with unprecedented precision. This is the future of intelligent high-capacity optical networks, and that future starts now. So, why we need a fundamentally new approach to design optical hardware? So first, the complexity of modern system is exploding. Today's transceivers combine optics, DSP, PIC, RF chain, CPU, and FPGAs, are tightly coupled and interacting across domains. So as we move toward 1.6 terabyte system and even 3.2 terabyte platforms, so classical tools simply cannot capture this non-linear multi-domain behavior with sufficient accuracy. Second, classical simulation is hitting a wall. It's slow, it is expensive, and it cannot scale to the massive state space of next generation hardware. Multi-hour or multi-day simulations have become a bottleneck in design, verification, and manufacturing. So it is clear that optical hardware has become too complex for classical methods. Digital twins are essential, but only quantum-enabled digital twins have the power to emulate future systems with the fidelity and speed required. This is the foundation for the next generation of optical innovation. So to understand why quantum-enabled digital twins are so powerful, we must first understand what a digital twin really is. So a digital twin, a digital twin is not just a simulation. It is a living virtual replica of physical system. It behaves like real hardware, reacts to conditions, and evolves over time. In industries from aerospace to telecom, digital twins let engineers test millions of scenarios without touching the actual device. A key feature is continuous synchronization. Real telemetry of DSP states flows into the twin, keeping it perfectly aligned with its physical counterpart. This enables predictive maintenance, instant diagnostics, optimized operating points, and safe exploration of extreme conditions. Digital twins dramatically reduce prototyping time and operational cost because engineers can run thousands of virtual experiments instead of expensive time-consuming lab tests. So this is the real-life jet engine example for digital twin. So as you can see, we have physical and we have digital twin for the jet engine. So this is not a fiction picture; it's a real industry picture that I have got it. So now that we know that what a digital twin is, the next question is why our classical digital twins are no longer enough? So the answer lies in increasing complexity of modern optical systems. The first classical twin cannot scale to model nonlinear optical physics, quantum noise, and the effects like current distortions, Raman interactions, and coherent detection noise are simply too complex for replication systems. Second, today's coherent transceivers rely on extremely heavy DSP pipeline and algorithms performing millions of operations per second. Emulating these in real time is far beyond the capability of classical simulations. Third, as hardware integrates PIC, DSP, ASIC, and RF chain, the system's state space explodes. Classical models collapse under the weight of high-dimensional interactions and cross-layer feedback loops. And finally, classical simulation often requires minutes, hours, or even days to produce system-level results. This is unacceptable when designing 800G system or 1.6 terabyte system that demand instantaneous prediction and rapid prototyping. So classical instructions cannot keep up nonlinear physics, massive DSP workloads, exploding state space, and long compute times limit their effectiveness. This is basically where quantum intelligence become a game changer. So let's discuss why quantum computing is not just a faster computer. It is a fundamentally the right technology for modeling next generation optical systems. Modern current optics, peaks, amplifiers, and nonlinear fiber links all operate at the quantum level. Classical computers try to approximate these behaviors using complex numerical methods, but they quickly hit a wall. Quantum computers, by contrast, natively represent quantum states, which makes them inherently aligned with optical physics. They can accurately model phenomena like hazy noise, phase noise, four-wave mixing, Raman scattering, and photon-to-photon interactions. Effects that are nearly impossible to simulate classically because they are probabilistic and multidimensional. Quantum hardware naturally evolves these noise operators, producing simulations that better match real hardware behavior. Another major advantage is scalability. Optical systems contain enormous state space, multiple wavelengths, polarization, DSP state, temperature drift, non-linearities. Classical simulators choke as dimensions multiply, but a quantum computer represents truth for any state with just n qubits, which means it can scale effortlessly where classical approaches collapse. And finally, quantum systems evaluate many possible systems trajectories in parallel through superposition instead of running thousands of simulations. Sequentially, a quantum simulator stores multiple noise parts, power settings, and design variations at once. That means after optimization, faster diagnosis and much higher fidelity predictions are possible. So let me bring all pieces together and show you the vision behind the quantum-enabled digital twin. It is traditional digital twin is already powerful, but in the systems we build today, it is no longer enough. So we redefine it as a combination of classical machine learning, quantum simulation, and real hardware telemetry working in unison. Classical AI learns patterns of behavior, how the hardware normally operates, how it drifts, how it ages. But AI alone does not understand the deep physics underneath. That's where the quantum computers come in. It models the nonlinearities, the noise, the interaction that classical tools simply cannot compute at scale. Real hardware then closes the loop, providing continuous calibration, real-time feedback, and grounding the model in reality. And when these three elements come together, AI, quantum physics, and hardware telemetry, we get a unified digital twin that can predict hardware behavior even under conditions no engineer has ever tested. This is the future, a digital twin that does not just mirror the system, but anticipates how it behaves, adapts in real time, and unlocks a completely new generation of optical and embedded systems. So this slide shows how quantum computing fundamentally transforms the way we model, simulate, and emulate modern optical hardware. First, quantum computing radically improves modeling of coherent transceivers. These systems rely on phase and amplitude modulation, polarization multiplexing, DSP equalization, and nonlinear physics. These are phenomena that are quantum in nature. By presenting optical states directly with qubits, quantum computers create digital twins that are dramatically more accurate for 400G, 800G, and 1.6 terabyte coherent models. Second, quantum computing excels in simulating quantum noise. Classical simulators approximate these effects with enormous numerical effort, but quantum simulators compute them natively because the noise operators evolve inside the quantum state itself. This leads to far more realistic predictions. Third, quantum hardware enables emulation of peak components. Since these devices rely on interference and quantum processors are a natural match. This reduces prototyping cycles and allows teams to test virtual peaks before fabrication. And finally, quantum computers allow us to explore DSP optimization in parallel. DSP algorithms and nonlinear compensation are extremely compute heavy. Quantum systems evaluate multiple DSP trajectories simultaneously. dramatically reducing time to solution. Alright, so to understand why quantum computing is so powerful for optical systems, we need to look at the language of the physics itself, that's the Hamiltonians. So Hamiltonians are the blueprint of how physical systems behave. Every optical or RF device, a laser, a fiber, a photonic chip, and amplifier, can be described by a Hamiltonian that details how the system evolves in time. Classical historians try to approximate this evolution using heavy numerical formulas, but for quantum computers, Hamiltonians are native. They are machines' natural operating language. This is why quantum computing aligns so perfectly with optical physics. Classical models only approximate hardware. Quantum models become the hardware. By using Hamiltonians and Lindblad operators, quantum computing enables digital twins with true physical level accuracy, opening the door to breakthroughs in optical, RF, and photonic system design. Quantum simulators gives us something we have never had before, the ability to emulate real optical hardware before we build it. Instead of fabricating a Mach-Zehnder modulator or a ring resonator and waiting weeks to see if it works, a quantum simulator can model a interference, phase shifts, non-unities, resonance drift, and thermal noise with physics-level accuracy. It can even emulate 90-degree hybrids, SOS, amplifiers, and full-peak mixing behavior, capturing AC noise, carrier dynamics, and quantum interference that classical solvers struggle with. This means we can design, tune, and validate entire photonic chips virtually, exploring thousands of variations in minutes instead of the months. So here is how a modern digital twin really works and why combining classical ML with quantum simulation is so powerful. First, we continuously collect live telemetry from actual optical hardware like OSNR, bit error rate, bias drift, temperature, speed states. This becomes the heartbeat of the device. Next, a classical machine learning model learns behavior patterns, how the system treats, how it ages, and what normal looks like. But ML alone cannot capture the physics. That's where the quantum simulator comes in. It injects quantum accurate effects, non-linearities, phase noise, current interference, giving the twin a level of realism. When we combine ML's behavior intelligence with quantum physics modeling, we get a hybrid engine that can forecast degradation, detect anomalies early, and predict failures before they happen. The digital twin updates itself continuously, becoming a self-optimizing virtual copy of the hardware, always learning, always anticipating, always staying one step ahead. So let's look at what digital twins actually do in the real operating system, because their impact is not theoretical, it's transformative. First, digital twins predict Raman gain tilt and nonlinear distortions before they harm link. They sense OSNR changes, detect subtle amplifier drift, and warn early, giving the network something like a sixth sense. Second, digital twins detect real-time drift in high-speed coherent transceivers at hundreds of gigabaud. Tiny bias shifts, laser aging, or temperature fluctuations can break DSP convergence so easily. The twin continuously compares real behavior to the virtual model and reflects the moment something starts to go off track. Third, digital twins automatically twin modulator bias points. Mach-Zehnder modulators are extremely sensitive. Small drifts degrade Q and increase bit error rate. The twin predicts the drift and centers the bias automatically. No manual tweaking required. Fourth, in peak manufacturing, digital twins allow engineers to test thousands of design variations virtually, like waveguide, widths, coupler ratios, resonator, geometries, letting you fabricate only the optimal design and avoid costly wafer re-space. And finally, digital twins cut lab testing by 70 to 80% instead of endless sweeps and measurements. Engineers enter the lab knowing exactly what will work because the twin already explored the impairment case. A coherent GR plus transceiver is one of the most complex pieces of optical hardware that we are building. A quantum enhanced digital twin becomes its full virtual replica, modeling GSP behavior, polarization impairments, phase noise, and nonlinear effects with physics level accuracy. It lets us predict failures, optimize performance, and rehearse the model's entire lifetime before it's even manufactured. This is the future of coherent optics. So, so as exciting as quantum-enabled digital twins are, we must also recognize today's challenges. Current quantum processors still have limited qubit counts, so large optical models require hybrid approaches and clever circuit design. But this is temporary because qubit capacity is growing rapidly day by day. The NISP devices also introduce noise and
Good morning, everyone. I request all the dignitaries to please be seated on the dais. Thank you. Us virtually from Nokia of America Corporation, USA. Before we begin the minute, good afternoon, everyone.